Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good day. Thank you to Associate Professor Dr. Wan Naim for your kind introduction. I'm glad today I got invited to share some inputs, basically to all geospatial community in Malaysia on something that I have been really working on and involved with. So let's not delay any further. Today I would like to share with you some inputs on leveraging geospatial technology and numerical simulation models for urban environmental planning. Or specifically, I would say I'm working with urban climate studies. Honestly, I must have started playing, not really working with these numerical simulations about 8 years ago, when I'm actually scratching for my PhD and research topic. So only then I realized there is so much to learn and there are so many opportunities to look into. So this is the skeletons of the presentation. What will be in my presentation will be a brief introduction on geospatial technology research and opportunity in numerical simulation models, followed by a very short introduction on numerical simulation models. I will try to highlight the G's of us, the G's of geospatial in numerical models, and what both fields could benefit by each other's existence. There's no math, there's no equation, there's no formula, no worries. Yeah? And then the integration and the outcomes, which there will be some examples of existing research and how do they actually do a calibration and how do they modify and utilize geospatial data in numerical simulation models. And finally, some future directions, which of course we will reflect that with the Sustainable Development Goals. Right, ladies and gentlemen, I believe in this hall, geospatial need no introductions. It's a geospatial community, so I guess all of us is already the expert in geospatial technology. Whether we realize it or not, researchers all over the world, whether they have realized, they have used a combination of geospatial technology in their research, may it be in the field of engineering, geotechnics, or social science and health. Satellite imagery and field measurement coupled with statistical modeling to calculate and solve worldwide environment problem in looking for solution, remedy, and monitoring for betterment of for the society. Moving on the current trends of geospatial, geospatial technology, as it is commonly known, is multidisciplinary tools that are now spearheading the effort in solving the 21st century problems and challenges. We cannot get away with the location issue, and consequently, we cannot get away from how the things that happen may or may not affect us. The clue is actually in the word geography. Okay, because whether we like it or not, whether we understand it or appreciate it or not, geography is vital and important in our everyday lives. Questions such as, what is the geographic distribution of certain endangered species? Or how do we plot the migrating populations from certain area? How can we predict a new oil pockets that might exist based on the data of the past oil pockets and the current existing data? How has a particular landscape eroded over the last number of years? And will this erosion be in danger to the existing settlement and in any time soon? And which country or cities and area are the biggest polluters? What can we do with it? And how can we plan our city to minimize pollutions of a certain areas? Now, with these revolutions of geospatial technology trends, such as big data, cloud computing, IR 4.0s, wireless and stuff, geospatial analysis can be done easily, even with a minimal knowledge of smart computing. Because of the ease of use of computer system nowadays. And with that, geospatial community have grown significantly over the years. Now, as the title indicated, allow me to set the notion on the brief introduction of what is numerical simulations, particularly the one type that I've been working with, the numerical weather production model. It is basically a set of equations that describe the dynamics and thermodynamics of process in the Earth's atmosphere. Basically, it predicts through numerical simulation that is based on physics options that is available from the data provider, which is we can actually predict as far as a month. And usually a weather forecast is being given region and has a definite time of period probability. Every physics options basically used or set or configured in advance before we start the simulations may slightly be differ from one simulation to another simulation. This is why it's because of the application to different parts of the world and also focus on different kind of atmospheric process, different time and spatial scales, ambiguity and uncertainty of the formulations, and also it is tailored to a certain purpose of studies. These are basically the basic equations applied, not in the form of equation. It's a text. So to many different types of atmospheric model, such as appear in this list. And this one is basically how it is being scaled to, by the numerical weather prediction models. We have 4 types of scales: global, synoptic, meso, and micro-urban. I guess this is actually how it is represented according to the satellite image also, because we have different scales of satellite image. Right. There are also many other available numerical models that could potentially be used to integrate, modify, and configure with localized data. Most of these numerical simulation model that is being developed by National Center of Atmospheric Research and most of the centers all over the world basically is being set into a default by the data that is provided by NASA and any other departments that is basically the provider or the developer of the models. So what this model can do, basically these are the summary of the functions basically of these numerical simulations. We have in table here 6 numerical simulation, which is most of them have the capability to model atmospheric, oceanic modeling, and also climate projections. I think one of the speakers here is from Nahrim. I think Nahrim, if you are familiar with PRECIS, many of Nahrim reports is actually being used PRECIS as their simulation software. And then we go into this 4. Basically, this is another 4 model, ADRIC. It's widely used to predict storm water level and to help control the impact and storm damage, such as hurricane, flood, and thunderstorm. We have AMOD, which is a mathematical simulation of physics and chemistry governing the transport, dispersion, and transformation of pollutants in the atmosphere, as well as estimating downwind pollutions and concentration. Now, we move to MM5 and WRF. MM5 is Mesoscale Model 5, and WRF stands for Weather Research and Forecasting Models. These 2 models is basically the one that I have been using in most of my research studies. And this model are basically a system model. It was developed by the same agency, the National Center for Atmospheric Research, and both is being maintained by different agencies, M5 being with Penn State University and Weather Research Forecast as the list you see on the table. Right, some example of the snapshot of the user interface of these numerical simulation models, and some example of input. And again, if you're familiar with some of the Nahrim's report, you may find PRECIS interface is very familiar one. Right, now let me focus on WRF, as this is the main numerical tool that I've been used in most of my climate study. Right, let me be honest with you, I also need a battalion of army to help me to understand this. So I didn't expect everybody to understand it just in one presentation. So, but I'm quite clear that the benefits and what could we be getting from it. WRF is basically a next generation mesoscale numerical weather prediction, basically designed to both atmospheric research and operational forecasting. It is actually contains of 2 core, which is the advanced research, weather research and forecasting, and also another one is non-hydrostatic mesoscale model, right? So in WRF, basically, before we start working with WRF, it's involved some calibrations or configuration, where this is where geospatial data is very crucial, right? Because it involves geospatial data as data inputs within the system. If we are using the numerical simulation model as it is, we are actually using a default configuration, which is, it is not correctly represented the area or the locality conditions of where the study areas is. So if you look into the slides, very small text that I have bold here is basically those are the area where we could input some of our spatial data, where we could use it to calibrate and to reconfigure the settings of the numerical simulations. WRF, one of it is WRF terrestrial data. This is actually where the geographic data can further be modified, can be manipulated by using localized data configurations. So as the output of the numerical simulation, we usually will choose grid or NetCDF format, in which we could further manipulate or analyze this data in ArcGIS software or any other software available online. So hence, geospatial comes as a configuration input, as well as the output, which can be further explored and integrated with any purpose of urban climate study, or in fact any other kind of studies. Now, this is basically some of the case study that have been conducted. For this case study, there the modification values is only done by changing the values of land surface albedo within the configurations. Okay, that small change actually brings so much difference in the configuration. I think some of the text in the slide is missing. Now, in this particular study, which was conducted in Putrajaya, the land use of Putrajaya was classified using this remote sensing software. But if we are using the default configuration, the land use of Putrajaya is actually being classified as deciduous needle-leaf forest, which clearly being misclassified. So what we do is we calibrate and we change the value of land we give them an input value of current, or the most current land use and land cover, and we change the value of land surface albedo. Then here, these are basically the data input, which is obviously what we could offer to this community, to this numerical community. What we could offer to them is basically we give them a validated remotely sensed data. We are rich with the spatially consistent, spatially and temporally consistent data. So this is where we could strike in integrating numerical simulation models. So after the modification, basically we could see that the original, the default configuration of numerical simulation results with the modified numerical simulation configurations, a result is improved. Basically, we compare it with the land surface temperature map produced by Landsat, and also we compare it with the CAQMs, continuous air quality monitoring station data. So we see lots of improvement in terms of patterns and trends, and also the value of the, for this case, is the air temperature and the land surface temperature. So it is not only restricted to land use and land cover. We could also input any sort of geospatial data, as long as the data is prepared in grid form or in a pixel form, where we can actually convert the data into a binary form. Okay? As long as the data can be converted into binary form, we can feed the data inside WRF, and then we can run the simulation again with the localized values. Right, this is another studies, results from, again, a modification through the land surface, land use and land cover. So what is actually being tested here? We also compared the result with the land surface model established by other parts of the country. So for this one, we use NOAA LSM, which is land surface model established, and also urban canopy models. Okay? And we injected a new, an updated land use and land cover generated from satellite imagery. Now, we see that the model successfully employ the urban, and we have found that an updated terrestrial land use map is developed for Selangor to better represent the diversification of urban land cover. And greater improvement basically can be seen in the model result near surface condition is observed by updating the land use map than the UCM. So this figure here basically shows that the performance of the best 4 cases, basically they are improved in terms of the accuracy. Here we measured 2-meter temperature, which represented as air temperature, 2-meter relative humidity, 10-meter wind speed, and TSK, and they are all improved by the numbers that is presented respectively. Now, ladies and gentlemen, the potential integration, again, is not just limited to land use data. We can also incorporate other data such as building density, height, roughness length, any other information such as all physics properties of the area. So in my previous slide, because most of the model calibration was done using a modified land use and land surface albedo, so there are many opportunities to further modify these models. So and finally, this is basically adopted by Chow Ren, which is the urban climate scientist from Hong Kong, whom her team has established their very own comprehensive urban climatic map by utilizing full capacity of geospatial data in terms of geographic terrain informations and greenery and planning parameters. What they do, they couple this information with the computational parameters that is defined to define their climatopes and cold air collections areas, and thus they produce their first urban climatic map analysis. From here, basically planning recommendation can be made, can be identified, and planning decisions and instruction can be wisely put forward. This is how we could integrate geospatial technology and numerical simulation model for urban climate study and climate analysis. Now, almost done. As modeling and mapping has become more temporal and spatially demanding, the integration of numerical models such as WRF with geospatial technology has been a great complement and to enhance and fill the gaps and shortcomings of each other, especially in fitting into urban scale study, temporal flexibility, as well as in getting the complete spatial coverage. Geospatial, with its comprehensive archives and consistent temporal observation through satellite image, enable time series and analysis to be conducted, and high accuracy data input for terrain and real-time observation can be obtained. For numerical simulation, with its rich mathematical modeling, is able to produce high accuracy time series, data from global to microclimate scales for various climate studies. The availability of this numerical simulation model for free should be leveraged by us, the geospatialist community, in order to bring more flexibility in framing and analyzing the situation of urban environmental planning, so to help and assist stakeholder and policymaker to make informed decisions so as to fulfill the new urban agenda.
Ada 10 saat saja lagi.
Yes. My last slide. This is my last slide. So in short, it is at urge, basically, for Malaysia, for us, to have our very own urban climatic map that will further assist policymaker and urban developer to make a right decision after taking all the key climate parameters into consideration. I hope for this sharing and a new important research opportunity has been brought to light. With that, I end my presentation with this slide. Assalamualaikum.